individual sections of the system to kind of maybe put it together and just throw it up and around. The compressed air industry tends to look from the compressor room out. And I'm not saying that that's a bad thing, it's important, right? On the other side, the pneumatics industry starts on the opposite end of the system. And they're optimizing those individual processes, and they look into the distribution from the opposite side. But there's almost like this no man's land in the middle. And my daughter doesn't know this, but I'm going to have to tell her that one of the things that, the example that always comes to mind is when she asked me to go take her to get a boba tea, and they've got these little tapioca things, and I can't get them up through the straw. And you think about no matter how good it is on one side or the other, if you can't get it across, you're done. So ISO 11011 will say that we have supply, distribution, and the demand. In my experience, there are 8 sections to a compressed air system. One of the arguments that we have, like if we look at like the ISO models, though, is we talk about boundaries here. So for the purpose of this thought process, excuse the boundaries. Let's take the boundaries off the compressed air system and say, hey, before we ever get to the air compressors, we already have challenges. A couple people earlier today have already talked about the air in the room, the temperature in the room, the electricity coming to the compressor. Now, we do have very real arguments when we say, hey, where does the compressed air system start? We can't say, hey, is the coal miner shoveling enough to be efficient, right? So where is the line? But it affects it. If you go into a compressor station and you can't open the door, you might have a little issue, right? And it goes all the way through. No one is an expert in all of them. In fact, as I've developed this over the years, the thing that it taught me is that I'm not that smart. And my friend and colleague Menno will challenge me, and he gets grumpy when I call myself stupid. But I'd like to say that if you embrace a lack of knowledge, what ends up happening is you're open to everything and anything that comes your way. One of the things I found that's a mistake that I tend to make when I'm auditing systems is I'll see something that I think I've seen before. And then I go down this path because I think I know what the answer is, and I'm usually wrong. So for me, separating the system out in 8 pieces has been instrumental in assessment and overall optimization of compressed air systems. I see how easy it is to press that button twice. Where'd that gentleman go? Yeah. So the cost of getting it wrong. If we don't design the system right, if we don't purchase the right things and we don't build it properly, it affects everything all the way through to our process, including our products. The risk zones of compressed air systems, piping size affects all of them a little bit the same, but also very much differently. One of the key things here is that inside the process equipment is a micro version of your distribution network. Everything we look at, from pipe size, pipe design, how we move air from the compressor room through the distribution, that is mirrored on a micro level inside the processes. There you will see thousands, millions of examples where a cylinder only requires 1 bar. But it takes 6 bar to get through 4 kilometers of 6 millimeter tubing inside the machine. That is a micro level of the same things that we work on the distribution. But in the compressor room, we think about pressure fluctuation, the ability of the air to get through the room, inadequate piping, multiple elbows and T's and valves. All of these things are affecting the ability of the compressed air supply to respond to the demand profile. And we make it harder than it has to be if we don't take it into account. On the distribution, one of the interesting things on the distribution, I guess this falls in all of it, is transient flow. We're going to talk about that a little bit later. Not just static volumes going through your system, but the real world changes in volume requirements of the plant. Personality. One of the things when we're training young air compressor technicians is that there's really, in my humble experience, is there's a component level, there's an equipment level, and then there's a system level. And while we're troubleshooting things, you might look and say, hey, this inlet valve or this solenoid valve isn't doing what it's supposed to be doing. But if it breaks once every 3 months for 2 years, do you think it's the valve? It might not be, right? It could be an idiosyncrasy of a piece of equipment, but realistically, of all the manufacturers of compressors that I've ever had the pleasure of working with, they all care pretty much. They all work hard, and they really build quality products. It's the utilization of the products in the system level that causes so many problems when you look at repeating issues. But when you consider how your system operates, consider that the personality of the system is something to train your people on. If it's hypersensitive, right? One small little change and all of a sudden it goes down. Or if it's slow to respond, all of these things mirror human personalities, and it's a good thing to have in the back of your head when you're trying to figure out what the problem is in your system. My friend, Mr. Godfrey, I was feeling a little grumpy if I gotta tell you the truth. I'd been called to a plant that was very, very far away in a very, very rural area. And the corporate level, for any of you guys that do assessments and audits for a living, sometimes the corporate directives don't match the plant level directives. So the corporate level was very much for paying me to go out there. The plant level couldn't see why there was a problem. So it got a little funky, and we ended up waiting for almost 4 hours in the conference room before they'd even let us get to work. But Mr. Godke was talking about how and I want to say the young lady from Kaiser talked about it this morning. She talked about how people are afraid of pressure, right? The overpressurization due to fear, right? The people working in the plant are more sensitive to pressure than the actual equipment is. So when we talk about pressure drop, there really is only one equation, right? The American version of this is a little bit different. In fact, when I at a last minute thought, I was like, I wonder if this is a little bit different in Europe. And I checked it because ours as a rule of thumb in university, we learned flavor squared over 2 dog Charlie. And that's just how we memorize the equation. Turns out it's a little different for y'all over here. But the critical thing about the equation is that diameter, velocity, those are the big things. Those are what's going to affect you throughout your system in everything, from the fittings to the valves to the piping. So we can have a science class, but in the short, diameter of pipe, velocity, these are things that we have to fight to get the air to where it needs to go. One of the methods that people can use on the fly is called the equivalent length method. Has anybody ever used equivalent length? Not really compressed air? Yeah. Okay, so you have, right? Yeah. I will tell you, you're basically adding up a value. So your fitting based on a flow rate will have a value of straight pipe. And so it might be 1.5 feet, or so then you would do your calculations based on the extent, the new length or effective length of the fittings. It has its limitations, but it is definitely enough. Using the Moody chart, knowing the Reynolds number and the relative pipe roughness. How often do we in our industry consider the roughness of the piping material, or how that changes over time? It does. Yeah, in fact, if you looked up Schedule 40 black, it would show you new and then on. One of the interesting things about here is if you start looking up Reynolds numbers in your calculations, you're going to find that it's really hard to be anything but super fast air. So compressed air is relatively almost never Lambert. It's just fast. The K-factor method is something some of our colleagues, Dr. Elvira and Danny, are working on building out K-factors for different valves and fittings in our industry. The K-factor is very similar to the CV value in water, but the K-factor basically considers the friction and the effective length for each component that goes in the pipe, but still taking into account the length and diameter and then the velocity through. We talk about these things a little bit, but I really just don't want to live here. Like, we've all been there, we've all had this class, and we were all way too young and probably stayed out way too late the night before while in this class. But there are different methods of doing this, and depending on how close and exacting you want to be is going to drive you to which way you want to go. And remember, as always, if you're not going to be the expert, hire them. Computational fluid dynamics, more than just a buzzword. The younger engineers are doing some really great stuff with this. Nothing that I understand, so we'll move through because Jan fell off a bicycle and can't help it. But velocity. It's overlooked. It's just overlooked. When you talk about static flow, if you assume that there is just a constant volume of air moving through your pipe at all times, you're going to miss the mark. So what flow rate do you use if you're designing a pipe size? The size of the compressor discharge? That'd be good for the whole system, right? What do? Are you adding up the flow rates of all of the compressors? We had conversations about N+1, N+2, 2N. Are you doing it based on that? What flow rate are you using? I will tell you, for everybody in this room, we've probably seen millions of assessments and graphs. How many of those flow rates were like this? 0? Is the air in your system, did the air in your system go to the same elementary school as you? Does it move once per second? Or once per minute? Or does it equalize as there's a change of pressure? It didn't take the elementary school class. So if we say that you're 10 cubic meters per minute, if it's rated for 10 cubic meters per minute, but the cycle is every once a second, if you get 10 cubic meters in 1 second and then nothing for 59, you are 1/60th of the pipe size that you should have had for that instance, because you didn't take into account the cycle rate of the flow. In the compressor room, variable capacity of air compressors, wet receiver tanks, and God knows, dryer controls in the olden days, every one of us was taught to put wet receivers in front of the dryers. Maybe that's the right thing to do, maybe not. I've seen people go to blows over that. There's no reason to talk about that here, but it is important to say if you have a storage volume of air upstream of your dryer and filtration, you cannot size the dryer and filtration solely based on the compressor discharge. Because now you have an intermittent demand available. You have a battery there up, right? And now that will cause swings in your air quality. Secondary storage. How much secondary storage? The question is, are you taking it from the compressor or are you taking it from the system? The process equipment, uneven demand profiles, changes in production. When you change production, how much of your air is constant and what machinery do you have in your plant that changes the air requirements when that production changes? Intermittent demand changes the pressure control. Has anybody ever seen a pressure regulator not working? Yeah, me neither. Has anybody ever seen a pressure regulator that was turned up because the operator didn't think it was good enough? Yeah, me neither. So, not to mention, how do the processes break? The favorite example would be dust collectors, right? You get a small cyclic amount of air, but if and when that breaks, it changes the dynamic of your whole system. Receiver tanks sometimes are just oversimplified. Receiver tanks have multiple different uses in a system, and some of them are Band-Aids. Well, my pipe's too small, big tank here, right? Not always are they a positive. Many times I'll go into a facility and do an assessment, and I'll see process tanks peppered somewhere or a big receiver in the corner, and I know they're trying to overcome something. But one of my favorite questions is, oh, did you buy that at the same time you built the plant? No, why do you ask? Just wondering. But understanding what you're getting out of receivers and the requirement of pressure across it, differential pressure across it, is critical to how the system operates. But you're not going to get the value of it if it's not working the way it's designed. So let's look at some ways to distribute air. I want to say that one of the speakers this morning talked about different methods of doing piping layouts, and we were talking about the loop design being a better design, and it absolutely is. You start with the branch layout. In order for this to be successful, you really have to oversize that main header. Otherwise, changes in the demand profile from the close side to the distal side of the system just throws off everything and gives high inconsistency. If you loop it, you're able to balance that air across it better. Loop and ladder, now you're adding cross headers. Still similar. The piping size is still critical, but this does give you a better way to go. And what I would call the best is a loop and ladder with subloops. If you evaluate your processes for groups and outliers, then you can create a subloop of piping that you can monitor, you can affect the quality of it, you can affect the pressure of it, you can measure and monitor every aspect of it, but it is completely isolated from the other sections of the facility. There's also another key benefit. Because plants don't run for 5 years and shut down, one of the coolest things about the subloop is when you go into a facility that's 50 years old, you don't have to pay 8 million euros to put it back together correctly. You can take out and build a little subloop for a small process group, right? Have the proper size tie-in with whatever filtration, pressure control process tools, storage, whatever it is. And then you just cross-connect it into the existing headers. Rip out the old piping, the dirty 30, all the leaks, all the everything else, and you can optimize old systems using this design without capital expense. Your shutdown is minimal, and you can really take control byte by byte by byte. So I wanted to show, and it's a little small, at least for my eyes. I didn't think I needed glasses up here. I was wrong. But when we look at the different sizes of pipe between 50 millimeter and 70 millimeter and 100 millimeter and 150 millimeter, that same volume of air, it's not just velocity that changes, the pressure drop per 30 meters also changes. But remember, in a compressed air system, it's the processes that drive your pressure requirement. So everything you lose in the piping, you have to overcome. So you have to increase the output of your supply to overcome this. Now there is multiple references in our industry that say, pressure loss and distribution 10%, under 10%, or under 10 psi, or under 5 psi. But I challenge you all this. Why wouldn't we say that the reference line is 0? Why wouldn't we make our goal and expectation 0 bar difference, 0 PSID, with an understanding that any loss whatsoever is waste? Design the piping for peak. I'll tell you that as a mechanical contractor, one of the questions I ask is, what are you going to change in the next couple of years? Because the pipe pricing is not linear. Whatever you pay for 50 millimeter pipe is like 4% less than what you pay for 60. It's not linear, and the compressed air system, the compressors, last a lot less than the piping. How many plants do we go in that have 50-year-old piping? I mean, the pipe is there to stay. It's not a linear increase in cost. Evaluating for what the future could be makes sense to an extent. Size pipe for velocity, treat receiver tanks as tools, group processes, measure with intent, and design on purpose. I do want to say real quick, because I know I'm short, one of the things that I like to pay attention to or promote thought on is that there is a point in your system where air is coming in, and there is a point in your system where the air is leaving. But that point changes its location whether the system is operating in design criteria or not. If you design it where the fulcrum point of the system is at the discharge of the dry storage, primary storage, then if you're using too much air, then it might move that to the wet storage. And now you're ripping air that is not of proper quality through your system. If you have a process that breaks or isn't working right, you could be robbing air from other processes instead of taking it from the compressed air station, right? Thank you. Does anybody have any questions in my 32 seconds? And realistically, these are, if you really want to get into like piping and books and stuff, these are buy them. Maybe don't pay $700 for the book because you can't upload them for sure. Sir.
I have a set of questions, but when you start looking at peak demand on production equipment, is that where you're seeing opportunities to increase the output of the production equipment?
Oh my gosh. That's a great question.
Can you repeat it?
Part of that is going to have to be answered in the booth. You're talking about evaluating the requirements. The question was evaluating the requirements at the process point, and is that where we start evaluating peak demand and like manufacturing process limitations? I will make a very bold argument after saying that I really do appreciate all of you and love you all very much. I don't think any process ever should be seen from the compressor room. If you have a flow meter at the discharge of your compressor station, you should not see any process whatsoever. If you have, or you do, you have not designed the process, you have not used your process tools correctly. Because peak demand is directly due to inadequate piping and improper use of process tools. And anybody that wants to talk about that later, we're over in there. Anybody else? Thank you for not calling me stupid in front of my kids.